I'm going to talk a little bit about method development strategies and some of the key considerations that we see to help develop successful sample prep methods. So essentially, we define the analytes, whether that's given to us by a customer, have the possibility to identify the best analysis method. Not always the case depending on whether you're actually told what we need to use, understand the matrix considerations, and then move on to determine the best sample prep method to use. So in terms of target analytes, are they ionic, non-polar? That could make you determine which technique you use, GCMS or LCMS. Sensitivity, selectivity, or specificity. Do you go with a triple quad? Do you need to get to the really low levels? Sensitivity and selectivity is generally better on a triple quad. What type of data do you need? Is it confirmation or is it screening? Are you looking for knowns or unknowns? Again, can all drive you in a certain direction. What type of analyzer are you using? Triple quad, it could be an ion trap. You could be using high resolution systems. Ionization modes, well, we know GC typically use EICI. There are softer approaches with atmospheric pressure GC available these days. From an LC perspective, you have electrospray. APCI is the most common ionization modes. Electrospray definitely suffers from matrix effects slightly more than APCI, but again, it certainly comes down to what you need to achieve. You also have other options such as ECD, FID. So experimental design. So when we're developing any of these methods, right from the start, we set our experiments out in a certain way. So we'll always compare to a standard. So no matrix. It's essentially spiked into a solvent, your recovery solvent of choice. Then we'll compare the extraction. We'll take the pre-spiked samples, so spiked at the very beginning, and then we'll run the equivalent matrix blank through the system or through the cartridge. That will give us the post-spike in. So we'll post-spike there. So we call that fortified samples. And then various calculations, percent recovery is pretty much the spike divided by the fortified times 100. So you're essentially limiting the difference to the cartridge. Matrix factors can be calculated from this. So if you take your fortified sample versus the standard, then obviously you can get some sort of matrix factor there. That does actually take into consideration some of the evaporation conditions as well, so it's not specifically matrix factor alone, but that can be targeted slightly further. And then you always have your efficiency, your spike versus your standard, so total extraction efficiency. The beauty of this type of experiment, certainly when you're running development, it can quite quickly predict where you're having the problems. So not necessarily a recovery issue, could be a suppression issue, and by running these experiments, it's quite easy to predict where the problem actually lies. So if you move on to analyte properties, obviously extremely important considerations. You're looking at structures, functional groups, your pK or acid dissociation constants, partition coefficients for solubility, log P's. You can see there we have 3 different analytes. MMA at the top, which has a dicarboxylic acid. You have an amphetamine type structure, which has a basic drug, and then something which is zwitterionic, which has the best of both worlds. So again, can move you in a certain direction from an extraction perspective or ionization efficiency perspective, or even choice of technique. Matrix considerations. So it's really important to know your matrix. You don't want to come and get your matrix blues. Terrible effects depending on individual components. You know, matrix to matrix is very, very different. So you've got endogenous and exogenous types of components. endogenous within the matrix, things like proteins, salts, lipids, phospholipids, red blood cells, urine, could be urea, creatinine. Exogenous are generally added, excipients, dosing vehicles, anticoagulants or stabilizers can all have cause problems with your analytical methodology, suppression or enhancement effects. So sample preparation techniques. You've obviously got a toolbox. So here we've ordered these in terms of selectivity on the left. As the selectivity increase on the right, extract cleanliness. So non-selective will generally give you relatively dirty samples, and then you increase the selectivity of your sample preparation device and generally gives you better cleanliness of your samples. So starting at the top, filtration, filter plus, something that can be used for urine samples, can be used to filter blood samples as well. Not something that we've done a lot with blood. And then you have slightly better cleanup, where you have the various matrix scavenging. So your PPT plus, which is protein precipitation, PLD plus is the phospholipid depletion. And then specifically for urine is the DME plus, although it does remove phospholipids really well from blood samples also. So there's some improved cleanliness over the filtration. Then you have techniques such as liquid-liquid extraction, and then move into your various forms of SPE, non-polar, polar, everything from a C2 up to a C18, cyano, all silica phases. And then you have a more attentive option in terms of the polymeric. Supported liquid extraction is a really popular technique in the clinical industry. Forensics works really well compared to liquid-liquid extraction. And then you have the higher selectivity mixed mode SPE options, Evolute Express, the CX, AX, strong and weak anion and cation exchanges, and that's both on silica or polymeric. So we will talk a little bit about some of these options. Supported liquid extraction. So the technique is analogous to traditional liquid-liquid extraction. It has workflow advantages. So you're not mixing in direct contact two liquids for partitioning. Essentially, this is performed in a column or a plate. The packing material is a modified form of diatomaceous earth. So it doesn't give you any interaction as you'd expect with solid phase extraction. Essentially, all it does is act as a scaffold for your aqueous. So the mechanism, 3 steps, it's a load, weight, dilute. You take your pre-treated sample, you add that to the column with a pulse of vacuum or positive pressure. You don't get any flow through as you would with SPE. So there's no conditioning, no equilibration. You take your pre-treated sample and load on. Nothing flows through. The aqueous absorbs onto the phase, the diatomaceous earth. You wait 5 minutes, and then you add a water immiscible organic solvent which percolates through the bed under gravity. So it's very simple. A little bit of vacuum or positive pressure to pull the aliquot off towards the end, and that's the whole process taken care of in the space of 10 minutes or so, depending on number of samples. So typical solvents, dichloromethane, hexane, MTBE, ethyl acetate. What you have is on the flow through part with a solvent, you're essentially getting repeat liquid-liquid extractions. So if you were to think liquid-liquid, you'd apply 1 aliquot of organic solvent, mix it up, remove. Then you'd add another aliquot and then take that away. So you do multiple liquid to get the recovery and the efficiency. Here you're getting that repeat partitioning as the organic solvent moves down the bed. So it's an efficient liquid type process. So over the years we've put in method development chart really to help people. So depending if your drugs are acidic, neutral or basic, we generally suggest some generic pH pre-treatment to start with. Ultimately here you're looking to neutralize your target analytes. So when, as we said with a pKa, once your analytes are neutralized, they become less polar, so they're more amenable to partition into the water immiscible organic solvents that you'll use in this type of approach. So acidic drugs, we would typically pH the plasma or the urine with some acid to take the pH down. And neutral drugs can actually work at physiological pHs. So although we suggest pH around about neutrality, you can also just perform steroid analysis with spiking internal standard and then extracting. That can help to maximize the amount that you load on in terms of your matrix. And for basic drugs, you have the option of taking the pH up slightly. Unlike liquid-liquid extraction, the pH control isn't quite as critical. You do need to get your pH to be your targets to be slightly more towards neutrality, but because of the efficiency of the technique, it's less reliant on having that definitive 2 pH units above or below to neutralize your target analyte. 4 solvents that we typically suggest: MTBE, dichloromethane DCM, and then for slightly more polarity, DCM IPA in the 95:5 ratio, or ethyl acetate. So again, depending on the types of drugs you're looking for, would dictate which solvent. So type of results that you could expect. So from a protein perspective, again, we have a gel on the left-hand side, and you can see the proteins prefer to stay in the aqueous on the phase and don't extract into the water immiscible organic solvents. So it's fantastic for removing proteins from a biological sample. In terms of phospholipids, again, we've separated out the lyso versus the phospholipids there on the chromatogram. Basic drug extraction using MTBE as the extraction solvent, and you can see excellent removal. That's baseline. So these have all been normalized to the same level to show any differences. If you were looking at an acidic drug, formic acid pre-treatment with serum, plasma, and then extraction with DCM, again, you're seeing baseline. So very, very low level phospholipids coming off at all. So extremely clean. If you increase the polarity of your extraction slightly by using ethyl acetate, you do start to pull some of these interferences off. There are various ways to mitigate this. You use a slightly lower load volume, and that can completely remove these interferences again. Solid phase extraction, as I mentioned, you have various options. Use silica or polymeric, everything from polar to non-polar. If you're looking at hydrophobic interaction, reverse phase, retention mechanisms, anything C18, C8, evolute ABN is the polymeric option. And then more selectivity, you have options in terms of mixed mode SPE. Again, they will take into account the same reverse phase mechanism, but add an ion exchange group. And that could be strong, weak, cation, anion, silica or polymeric. So plenty of options there. From a processing perspective, a little bit more involved than supported liquid extraction. You condition your phase, you equilibrate them with a pH associated with your matrix, or your pH pre-treatment for your matrix. Load your sample, and then various wash steps prior to drying, and then eluting the phase, eluting with an appropriate solvent from the phase. So pH control is really determining the retention and the elution here, depending on your exact mechanism. So unlike SLE, where you don't have an interaction, the aqueous just stays on the phase, amenable for the partitioning. Here you are using some sort of interaction. So you can see, depending on your pore size of your sorbent, then the idea is that your proteins are excluded from waste. They're washed through. Your target analytes are having an interaction in the pores. You wash to remove your salts, your phospholipids, and so on and so forth. and then you elute your drugs in a relatively clean extract. So again, from a method development standpoint, just a quick flow chart. To start off, is your compound charged or neutral? If it's neutral, then you have the potential of using a reverse phase or hydrophobic interaction. Things like a C18 or an evolute express, hydro or micro ABN could be used. If you're looking at charged analytes, is the compound anionic or cationic? Is the compound strong or weak? If you've got an anion, if you've got a strong or weak acid. Weak acids, pKs typically anywhere between 2 and 8. Then you'd be looking at a mixed mode strong anion exchange sorbent, something like evolute express AX or the micro version. If you've got a strong acid, pKa's are pretty low, less than 2, then you're probably looking at a weak anion exchange mechanism. So something like a WAX phase. If your compound is a base or cationic, then weak bases could vary in terms of pKs. You'd typically be looking at a strong cation exchange mechanism, something like an evolute CX. Strong basic drug, then you would move towards a weak cation exchange mixed mode, a WCX. So in terms of the chemistry, I'm just going to detail here some of the polymeric options. Over the years, silicas have been widely used. A lot of the more recent phases are polymeric. They're a bit more robust. They don't suffer from drying out effects, so can be a bit more user-friendly and less finicky when you're actually performing your extraction. So from a non-polar chemistry, these are water-wettable polystyrene divinyl benzene type phases. The evolute express incorporates some hydroxy-functional oligomers to get that balance of polar versus non-polar. Particle sizes 30 or 50 micron. What we've done here is look at quite a small targeted pore size distribution of around about 40 angstrom, and that's to exclude a lot of the larger molecular weight interferences such as proteins. So you can see there polar groups, non-polar groups, and the ABN part stands for acids, bases, or neutrals. So if you have a wide variety of drugs, as you would in maybe a forensic, then this could be a good option. So you get a bit more overlap in terms of the types of phases you could look at. Solid phase extraction, mixed mode, strong exchanges. So you have a non-polar chemistry with a strong exchange group. So you have a dual interaction in a single column. So you're retained by the hydrophobic anion exchange. So if you're looking at weak acids, you'd be using anion exchange. Basic drugs, you'd be looking at the cation exchange. So the strong cation exchange here is a sulfonic acid, and you'd be looking at weak bases that could be ionized or neutralized. So essentially, these strong phases that you'd be looking at, the sulfonic acid here or the quaternary amine here, are permanently ionized. So retention is dictated by the pH of your extraction solvents. So in order to elute, you'd have to take the pH up on the base and neutralize. So 2% ammonia in methanol or acetonitrile will elute these. So they work really well, but if you do have pH sensitive compounds, then you can obviously have a slight problem depending on which way that is. Likewise with the quaternary amine, you're interacting with your carboxylic acid. Elution is performed by neutralizing the acid group, 2% formic acid in something like methanol. Weak exchanges, mixed mode, WAX and WCX. Again, same non-polar chemistry with weak ion exchange groups. So you have that dual interaction. Here you've got your generally primary, secondary amine there, which will be ionized, or your carboxylic acid functionality. And again, the WCX is targeted towards strong basic groups, or your WAX, strong acid groups. These can be quite versatile in terms of what you actually extract. So the good point with some of these weak exchanges, you have the option of running pH control where the retention is again dictated by pH, but you can turn the charge on your analytes on or off, and also on the phase. So pH control is a bit more critical for retention, but also then it does give you the option to be able to elute in an appropriate pH control if you have sensitive analytes. So it's just a sorbent screen-in plate that we came up with a few years ago. Again, it gives you two methods which will cover your groups, and generally you pair up your strong cation exchange with your weak anion. Will extract under very similar conditions. So if you are screening and you don't know what you've got, likewise with strong acid and weak cation, you can use generic methods that are very similar between the two. So you have the options there, typical volumes. So in conclusion, some of the considerations: know your analytes. Obviously structures, functional groups are very, very important, helps predict possible retention methods. Polarities and solubilities for solvent considerations, and stability for pH control. However, analyte panels may be the same between matrices. However, not all matrices are the same. You need to consider your matrix as well as your analyte. What interferences are you trying to avoid? How similar are they to your target analytes? And finally, generic methods give you a really good start point, but they may need subtle optimization. So don't just use a generic method and think it's going to give you perfect results.